So the data I'm going to be using is a simulated TSO observation with the MIRI low resolution spectrometer. So we're going to be working with a simulated exposure from the MIRI low resolution spectrometer and taking that step by step through the pipeline. Now, I'm showing you here just the table of contents for the notebook. There is the pipeline is a big beast. There is a lot to it, and it can be a steep learning curve. So I can't show you every detail for it in this relatively short presentation, but I really hope that with what I'm going to show you here, you have like an idea of how to do the basic stuff with the pipeline, do the basic like call sequences in Python, and to kind of give you the tools to know how to make some changes and everything, and give you the tools to do for figure out how to do things for yourself for your particular research. So we're using here the JWST calibration pipeline version 1.3.3, which is the current latest version that's released, which you can find in GitHub. And the data simulations were produced with MIRI-Sim, which is a publicly available software package developed by the MIRI European Consortium. And I've included there the URL link to information about MIRI-Sim. This is also publicly available. The latest version is 2.4.1, which is compatible with the JWST calibration pipeline version 1.3.3. The input for the simulation is very simple. I kind of loosely based it on an exoplanet host star. I didn't write down which one, I can't remember. But it's basically a simple stellar SED, which I've modeled as a black body function. So it's an incredibly simple signal that we have in this spectrum here. And I've given in this section here details about the observational setup. So important to note is we have 100 groups and 10 integrations. And the MIRI LRS TSOs are performed in a subarray that measures 416 rows by 72 columns. So it's a kind of long, skinny subarray on the detector. So this is really short exposure, of course. In practice, time series observations are often hundreds or thousands of integrations in length. But so I really wanted to keep this exposure fairly short to keep the data volume manageable, because we don't want to sit and wait for the calibration pipeline to take longer to run. So this is really just a kind of token data set with not a lot of scientific value in itself. You have to bear in mind a number of caveats as well of working with MIRI-Sim data. I won't go through everything that I've listed here in detail, but in general, it's a simulation. The details of the detector response, when you really go into if you're really going into high precision, can get incredibly complex. And so what's modeled in MIRI-Sim is not fully physically realistic. So these simulated data sets are really perfect for the kind of data exploration that we're showing here, and to learn about the data format and practice analysis methods. But they're not really appropriate for really trying to understand the detailed noise properties of the MIRI detectors, because they're just not modeled realistically enough. So do keep that in mind. MIRI-Sim simulations also lack, for now, a kind of fixed header flag to mark that an exposure is a time series observation. So this is something that we're going to put in manually in this notebook. But do keep that in mind. If you do use it for your own simulations, you have to kind of do that manually, because otherwise the pipeline won't flag the exposure as a TSO and will kind of go down a slightly different branch. There is also no transit signal in this simulation. So every integration is basically is modeling the same flux. Okay, so moving on, we are going to start running these cells here. So first of all, we have to import a number of packages. There are also some commands up here which set some environment variables for CRDS, which is the Calibration Reference Data System. We're going to be talking a bit more about CRDS further down. But this is also something that's specified in the installation instructions for the pipeline. So if you go to the GitHub for the pipeline, you'll see more information about this. And then we install a number of standard Python and packages and AstroPy and Matplotlib for plotting. And then in the third block down there, sorry, fourth block, we import a number of modules from the JWST calibration pipeline and an additional package called GWCS, which is Generalized World Coordinate System, which is also packaged with the calibration pipeline. And then we're also going to create an output directory just that we can put all our output files into to keep, to keep things kind of organized. That's just basic housekeeping. So retrieving and inspecting your data. So for an observational program, you're going to retrieve your data from the MAST archive hosted at STSCI. So MAST is the Mikulski archive for space telescopes, which if you have used Hubble data or data from a number of other missions, you are probably quite familiar with the interface to that. So you would query on a number of different parameters, the mission, the instrument, the program ID, etc. You will find there the uncalibrated data, and that's what we're going to start with here as well. But by default, when the data come down from the observatory, they are actually run through the entire pipeline. So when you search for your the observations from your program, you will actually see the full set of data products output from the calibration pipeline, stages 1 through 2 and 3. So that basic run kind of uses a number of default parameters and settings that the instrument teams have kind of defined as being, pretty good, and it will work, and you will have calibrated data at the end. But of course, like for your particular science, for your particular target, you may want to tweak some settings. You might want to experiment with turning steps on and off. And so to that end, you probably will want to run the entire pipeline or parts of the pipeline again yourself. And so the point of this notebook is to kind of help you understand how to do that. But do note that you will actually get output products from the pipeline in the archive when you go to find your data. Okay, so we are going to get the data, and we need this second line here. So this FITS file is just our exposure. So our observation is in a single exposure with 100 groups and 10 integrations. So we're going to read this in. And so this is just a plain FITS file, which you can use standard AstroPy FITS IO functionality to read that in. And I'm just going to show that here. And I'm printing out the info on the header data unit. So you can see you have 5 extensions, an empty primary extension with the header. And then we have the main kind of science data is in extension number 1, the science extension. And you can see the dimensions of that is 72 by 416 by 100 by 10. So 72 and 416 are the dimensions of the slitless prism subarray, and then 100 is the number of groups, and 10 is the number of integrations. Then we have a few additional extensions, so a placeholder for data quality flags, which Nestor will be talking about a bit more, and a couple of other extensions, which I'm not going to go into in detail here, but which are documented in JDocs. Just using plain, the AstroPy IO functionality and Matplotlib, we can take a look at the data. So here I have just taken one randomly chosen integration. So this is integration 8. And I have picked 3 random groups on that integration. So 25, 50, and 100. This is the last one in the integration. Just to kind of illustrate that that the principle that Nestor also described about how you read out the frames non-destructively, so that basically the throughout the integration, the flux continues to be collected on the detector. So you can kind of see how, you know, that kind of like builds up over those 100 groups. The two markers you can see on there are just two random pixels I picked, one on the spectrum itself and one, the magenta one is just on the background. And if we look a little bit closer on that, you can see that principle of the flux accumulating on the pixels. The cyan one which contains source and background, and the magenta one which contains just background. The mirror detectors are delightful in the multitude of weird effects they have. You know, it's a lot of fun trying to understand its behavior exactly. One of them is that the first integration is always a little bit offset from the others. So that this cyan one here that you see offset is the first integration. So you can see here, you know, flux accumulating. And so when we do the kind of what we call the ramp fitting and creating a slope image, that is literally, you know, fitting a slope to this kind of quasi-linear accumulation of flux. So that was just using the just general kind of AstroPy fits functionality. But with the JWST pipeline, we also have another way of working with the data called the data models. Now, these data models are basically kind of containers for the data, like they're specifically tailored to the JWST data. So it will the data models will automatically contain a lot of the metadata that's captured in fits headers, for example, and they offer quite like a lot of flexibility in how you work with the data as you're working with the pipeline as well. But a lot of the operations that we are demonstrating, it is a little bit sort of your own preference. Like you can do a lot of these things with general fits functionality and header keywords. We actually imported the data models module in our list of imports. This is just part of the JWST package. There are various kinds of data models available, things like image model, a cube model, a spec model. These all have their own definitions and schemas, but you don't need to know what kind of model your data is. You can just open it with datamodels.open. So we do that here. So F was our fits file name. And so we just do datamodels.open. And then you can print out some information about the schema. So it's telling you this is a ramp model with these dimensions, which we saw before. And it tells you what the file name was that this was generated from. And so this is just a snapshot of the data schema of this model. And so you can see it has kind of in a single glance, you can see it's got like the frames, groups, integrations, different extensions that are there, all different containers. The science data is here in this data attribute. So that's kind of where the actual kind of science data lives. Okay, let's go further down. I'm just showing here some kind of the attributes of the data model and how you can access that. And so a really nice thing is that if you know there's like a fits header keyword that's called that, you know, for what the filter is, but you're not quite sure which header that's in or how to look for that, you can actually use this this method called find fits keyword, and it will then tell you what to query. I've got a typo here. To find that particular setting. Oh, what happened? Oh, sorry. Now I've messed it up. I knew I shouldn't try to do something live and on the fly. So this print statements here are just kind of to kind of illustrate how you can access these attributes. And so here, this find fits keyword, then it's telling me like this is this meta.instrument.filter is what I need to look for in the data model to tell me what the filter is. But I need to edit this print statement here. So if we now try to recreate the previous plots just using the data models instead of the kind of AstroPy fits IO functionality. We can show this here. We don't need to spend too long on this. It's exactly the same, but it's just to illustrate how you would do that with the data models instead of what we showed before. The models have this attribute called meta, which is all kind of metadata, and that's particularly powerful. So in the next kind of block, I've just printed out some like print statements with where I access certain properties of the data through the metadata attributes, just to kind of give some examples. And this is also where the TSO visit attribute lives that we need to set from 0 to true for the pipeline to recognize that this is a TSO from the MiriSim data. So in the next code block, I just do that. So just to kind of show you how that would be done. So you can see you can print out the exposure times, the original file name, etc., etc. And so finally it says our TSO setting now reads true, so we are ready to go forward. I'm going to run the data through stage 1, Cal Detector 1, and this is really just to basic illustration of the call sequence of the pipeline, and show you some really basic things like how to change a reference file, or change a setting for one of the steps. There is a ton of documentation of this. I have included links very regularly to relevant pages of what we're doing, so feel free to explore that if you want more information. I've just written here in the text what the very basic call sequence is. So you have CalWeb detector 1.detector1pipeline.call. And for that call sequence, you can either use the fits file name as input, or you can read the file name into a data model and then pass that to the call, basically. So I'm going to use the data model, but so this would work just as well if I actually just wrote in the fits file name. So we're going to run this. The only extra settings I'm putting here are save results is true, so just to make sure that it saves the output, and tell it where to put the output in the directory that we created at the start. So that's just general housekeeping stuff. This is the only part of the pipeline that does take a little bit of time to run, particularly for a very lengthy time series. This would this part can be quite time consuming. And so the time series observations are actually, if they're very long, the files, the exposures are segmented. So they're broken up into kind of sub-files such that each of the segments is less than 2 gigabytes. So it is possible that even if you have a single exposure for your time series, that you end up getting several uncal files. And they would have some kind of like seg and then an index in the file name, and that's basically the reason, because otherwise this step here, this detector 1 step here, can take quite a long time. So you see here, all the steps are being instantiated. On the documentation page that I've linked in the text above here, you can see like what all the different steps are. Not all steps apply to every instrument or even mode within instrument. So it's good to always look at the documentation page to see for your particular instrument mode, like what are the actual steps that apply. You get here a bunch of outputs about all the different settings. Are we done here yet? There is also a way to have the output written to a log file if you don't want all the screen output. And so particularly if you're maybe doing a lot of calibration runs, it could be useful to actually create a log file to keep a good record of what you've run. And that's also illustrated in the documentation about how to do that. So I've printed out what the output product is. So the main output product is an image model. So this is a single 2-dimensional image generated from this file _rate.fits. Now, what that's done is it's actually co-added all the integrations together, which is what you would do for a normal observation that's not a time series, because then, you actually want to just bring all the integrations together to maximize the signal to noise. For TSOs, every integration is kind of its own observation. That is what forms your time series in a way. So we don't want that single two-dimensional image. What we want is a second output file, which has as extension _rate int.fits. So whenever you see the int.fits kind of file naming convention, that means that it contains the information for each integration. So to go forward, you have to make sure that you work with the rate int.fits file, and then the subsequent pipeline steps will also know that they need to do everything at the level of the integration rather than bin everything together. So I have then created a few plots here. So here I've actually plotted every single slope image for each integration. So we've got 10 in total for 10 integrations. And so each of these images is kind of a snapshot in units of dn per second of our target over time. And as you can see, the sort of background levels are a bit variable. The data are noisy, so that there are some changes there. So if you want to change settings or make changes to how a step is run, it's good to understand like what's actually kind of happening, what data goes into how a step is run. So how does a step know what parameters to use? Well, so this is defined in parameter files, which are in a format called ASDIF, ASDF. That stands for Advanced Scientific Data Format. You can open these files in a regular text editor, so they're pretty readable. And there is actually a Python package called ASDIF that also lets you kind of work with ASDIF files programmatically, and that's also packaged with the calibration pipeline. Personally, I would you can also edit all the steps like in the call sequence. So personally, I find it safer to do that than really start like editing the ASDIF files themselves. But you can look at them, and in principle, you can sort of create a custom file as well. If you want to kind of really dig into what the pipeline just did to your data, there is this method called get CRDS parameters that you can run on the output and that gives you a bunch of information about that. So we're going to do that here on the rate int output. And then you get this. So it gives you a bunch of information about different versions that were used. And sort of lots and lots of different metadata. And so particularly useful here is that it will tell you what steps were run, so complete or skipped, and tell you also what the pipeline version was that you used, which is good if that changed, and dates and things like that. Bunch of information also from the FITS headers. And then down here, importantly, it will give you a bunch of file names for the different steps. And so these will be reference files that the instrument teams have produced that were applied to the data for all these individual steps. And so this is kind of important to look at. So what's this CRDS acronym that we keep seeing? It is the JWST Calibration Reference Data System. You'll see that acronym a lot when you work with the pipeline. And so each version of the pipeline has like an associated CRDX context, what they call. And so this is kind of corresponds to a set of parameter files and reference files that specifically associated with that pipeline version. You will see that also on the calibration pipeline GitHub pages. You will see that referenced. There is a package called CRDS that also comes with the pipeline that lets you do CRDS operations programmatically. But I actually find it simplest to just go through the web interface, which the URL I've put there. And I've just listed some screenshots here. So when you click on that link, you get something like this. You see all the different instruments here. And so you could select MIRI, and then you would get like, a big database basically of lots of different reference files for different steps. And I show here if you find the Pars Detector 1 pipeline. So these are the ASDIF files that contain the parameters for the Detector 1 pipeline. And so you have one which is for non-TSOs, and you have one for TSOs specifically. And you can literally just right-click that file and then download it to your hard drive and look at it. It's really kind of as simple as that. So I kind of find that easier to try and than figuring out how to do that with the through the CRDS package in Python. So next up, I'm going to show how you would want to run a step with a different reference file. And the second small change I'm going to show in this next pipeline call is to switch on a step that is usually skipped for time series observations. I've written down like some justification why the last frame step is one that you might want to consider toggling and seeing depending on your science. But it's, I'm going to leave it at the last frame step is usually skipped for TSOs, and we are going to show here how to switch it on. And the same kind of syntax would apply for any other step, basically. I'm also going to not save the results for this because we're not going to continue with the output from this. But so we're just going to run this. There is a read noise file that is in the local directory that I'm going to override the one in CRDS, basically. So you can see when you do the pipeline call, as well as providing the input data model and the housekeeping stuff like where to save the results, you can have this steps keyword, which you then have like a dictionary where you can set for individual steps. You can set parameters like I want to override this one with a different reference file, or I want to skip this one, or I want to not skip this one. So there's lots of options there. Then the run's going to be exactly the same. We'll just wait for this to finish. So the read noise file is like, we're not going to look at the data output in particular. The read noise file, it's actually a copy of the existing one, so it's not going to do anything particularly different, but I hope this will illustrate just kind of how to make those changes. This particular step, we can look at some of the outputs, but this is then going to complete our next section of the looking at the Detector 1 pipeline and how to do these simple operations. That was stage 1 done. So the next stage is stage 2. So this is where we get to the spectroscopically specific steps. Detector 1 is generic between imaging and spectroscopy. Here is where we kind of branch off. So for imaging TSOs, you would go to image 2 pipeline here. There are various steps here. So the ones that would be applied to this particular data set to LRS TSOs, and again, this is could be a slightly different sequence between different instruments and modes, are the assigning a world coordinate system, assigning a source type, flat fielding, the photometric calibration, and then spectral extraction. So at the end of stage 2, you end up with flux calibrated extracted spectra. So what I'm going to demonstrate here is how to run the pipeline step by step. So previously we showed just the detector 1 pipeline.call, which runs through all the steps together. And we can do that here as well. So I've just written the call sequence in the text. You can just do spec2 pipeline.call with the same basic inputs, and that works. But sometimes you might want to run a step individually. And so here with spec2, I'm actually going to run through, I'm going to show how to do that. So you have to include some extra imports to import the actual steps themselves. And then our first step is assigning a world coordinate system. So this step is really important because it attaches a bunch of information to the data. It allows you to convert pixels to RA and DEC on the sky. And it also, for Spectra, attaches a wavelength, basically wavelength information to the data. But this is all kind of like captured in an extra extension to the data. So the science data themselves are not actually modified at all by this step. But it is kind of important because the assignment of wavelengths assumes that the target is at a very specific position on the detector. And we use target acquisition for TSOs with LRS to do that very precise placement of the target on that specific location to ensure that that wavelength calibration is anchored to the right position. But of course, there are things that can happen with with that placement. So if everything works perfectly, then we expect to have like an accuracy of about 1/10 of a pixel, and a pixel is 110 microarcseconds for Miri. But of course there could be like a problem with the input coordinates or proper motions. There could be like a bit of drifting throughout throughout very long exposure. That's something we really going to have to see during flight. But so that is something to keep in mind. But we're going to run the step and see how it works and what the output looks like. So this is very quick. It uses information about the optical distortion and about the wavelength calibration to assign that information. So we now have this output product called assign WCS step.fits. When you run the steps individually, they're going to create an output file by default that really has the name of the step in it, so you know exactly what it was created by. What the assign WCS step also does is it kind of defines a bounding box region, it's called, on the array. For Miri LRS TSOs, we're only using a very small subarray, so the bounding box is like almost exactly the same size as the subarray. If you have a mode where you're actually using like the entire full array, it really kind of just sort of narrows down where the calibrations will be applied, which is sort of the scientifically valuable region. And so using this using the metadata and the JWCS package, you can kind of visualize that. So in this cell block here, we are printing out the coordinates of the bounding box. I've overplotted them on the 2D array. So you can see here, this is the whole subarray, and then the red rectangle is where the bounding box is. And then using this JWCS functionality, I believe, here, yes. So you can, this function called grid from bounding box. So you can actually create a two-dimensional grid and then use the WCS information to convert XY pixels to RA, DEC, and wavelength. Now the coordinates in MiriSim data are kind of just dummy, so there's not much value in showing those. But here in this, for creating this plot here, you can see how I've created a 2D wavelength map. So you can really see kind of at a glance where the kind of wavelengths are. So in this case, you see here the wavelength increases from top to bottom. There's a few steps I'm going to run through without much comment because they're kind of straightforward. The source type just assigns a default value to the target unless it's specified otherwise from APT. But for Miri LRS, the default value is point. And this kind of then determines also how the spectral extraction will be done. But so this is just a straightforward, doesn't take long. And so I've printed out here the output, the value after the source type step is point. So the code now knows it's a point source. Similarly, flat fielding. So this uses one of the flat fields that we have available in CRDS. We're just going to run through that and not make any changes. The photometric calibration is the next step, so that's an important one. The main thing to say about this step is that for TSOs, it's another one that you may want to experiment with turning on or off. The aspect I mentioned in assigned WTS, where the wavelength gets attached to a very specific pixel position where it expects the target to be, but it doesn't necessarily mean the target is exactly at that location. The photometric calibration is anchored to wavelength, so is indirectly also anchored to that specific point. So if there are pointing offsets, that is going to affect the photometric calibration as well. And if there are pointing offsets that vary throughout the exposure, that is going to affect your kind of ability to retrieve a faint transit signal. So again, this is, we're going to run it here, but this is, for example, like one that, for TSO analysis specifically, for like transiting exoplanets, for example, you could switch off and it can still perform the spectral extraction on the data when they're not flux calibrated. This is again a very quick step to perform. Spec2 pipeline is very quick for MIRI LRS. And I'm printing out here the data units after this. So data units prior to the photon step is dN per second. Data units after the photon step is megajanskis per steradian. Then the final step here is extract 1D. So this is where we go from the 2D image to a one-dimensional spectrum. So this is definitely also a step that we have, that there's some things to say about. So here too, the step uses some very default settings that, are kind of like good enough, good enough to produce a spectrum. And so that default setting is just a fixed width aperture measuring 11 pixels across. And the step does perform like the wavelength dependent flux loss correction because you have the fixed width rectangle. So we're going to do the basic step with the basic parameters. And the output product, this X1D product, is called a multi-spec model, which is actually a list of spec models. So each integration, again, because it's done at the integration level, each integration has its own spec model that's then packaged in this container called a multi-spec model. We are going to produce, I'm going to show how to produce a plot of the extracted spectra. There's only 10, so I've plotted all of them. And so that doesn't really look like a stellar SED, might be what you're thinking. You see here the flux picking up quite a lot at longer wavelengths, and that is because we have not done any background subtraction. So that's basically the thermal background, which in all of MIRI's modes becomes, the longer your wavelengths are, the higher that background becomes. And this bump here at 8 microns is also kind of an artifact, so it's also not part of the source. So in the next cells, I'm going to show how you can actually perform the background subtraction as part of the spectral extraction, which is something that you might want to do. So if we run the CRDS parameters method, you can now see, because we've gone through stage 2 of the pipeline, this is like a bunch more information has been added to this. But if you look for the extract 1D metadata, it gives you the name of this reference file, which is a .json file. So that is also, JSON is also a text, just a normal text editor readable format. And we can download that file from CRDS. Here I've actually got a cell that demonstrates how you download it through Python. But as I said, it is actually just a kind of, so you have an example of how to do that. But as I said before, you can also just go to the CRDS website and right click and save it that way. And if we then print out that what's in that JSON file, again, you could just open this on a text editor. You can see it contains a number of parameters, quite a small number of parameters, both for the fixed slit and the slitless modes of LRS. And so it really just, it has this extraction width. It tells the software what the dispersion axis is for LRS. It's only got very basic stuff in it. And so this file we can edit to do more, to do different types of extraction. It's really worth looking at the documentation. I've linked it because it does actually have a lot of possibilities of advanced things. And there's even things in there that I haven't quite sort of played around with a lot myself. But so here I'm just going to show how to do this slightly differently. And so in your home directory, there is a new JSON file called MIRI-extract1d slitless with background. So you can have a look at that just in a text editor, and you can see some extra settings that I've put in there to do the background subtraction. So I've just defined effectively an 11 pixel wide rectangle away from the spectrum to use as the subtraction. And so I've just got one of these override statements. So override extract1d and then passed the new file name. The problem here, all these warnings that you see, is basically because our wavelength calibration files currently only cover 5 to 12 microns, and the array in principle does cover like from 4 to like 14. And so it basically says, and these are all nans right now because we don't have calibration values there. So it's kind of complaining that it can't find flux this is in those pixels for the background, but that's basically normal. And of course, a lot of these calibration files will all be updated after commissioning. So many pixels. Oh. All right. Then we can reproduce that same plot we made before. And so there you can see now this does look like a tail of a blackbody function. And we have removed the thermal background and that artifact at 8 microns. So that's that. Finally, I am going to demonstrate how to run the Spec2 pipeline end to end, because this does it produces slightly different output names. So it will produce as output a cal.fits and cal.ins.fits, as well as these extracted products. I could just show, but even though the file output names are slightly different, if you plot the extracted spectra, this is again not doing the background subtraction. They are identical, whether you run it end to end or step by step. And so the third section I'm going to leave for you. It basically goes through the TSO3 pipeline, which does a bit of extra cleaning of the data. It redoes the spectral extraction, and if your files were really big and they were segmented, TSO3 will actually merge all the segments together. So the main difference is if you had segmented spectra, then instead of having the extracted ones per segment, you will now get them kind of all packaged into one file, and you have the white light curve creation, so where it sums over a specific wavelength range in the spectrum. So it's really like a few higher level operations on the data. The key difference there is that you have to create what's called an association file rather than to provide as input for the step